Hey, John here. Let's take a quick look at the history of computing. This Wikipedia page is not too bad. Arguably, there are a lot of things that could be added to a discussion of computer history. If you want to read more, you're free to click on all these links, go to Wikipedia, or just Google computer history. There'll be mountains of material written on the topic, all right? I'm attributing this information came from Wikipedia on this page right here. I'll include a link to this on my faculty page in my lecture notes for your convenience. Okay, let's get down here and look at the beginning and the evolution. The word itself, computer, okay? It turns out before we had these machines that we called computers, the word computer was in everyday use. The word computer referred to a person that performed computations pretty much on paper. I'm going to add up a bunch of numbers, or I'm going to calculate, write down a multiplication table that someone can use to look up values and products. Well, that is a person. That person was referred to as a computer, okay? So that's kind of where the word came from. And then later on, once we started building actual machines that did the same task, the machines became the computer, right? So it's whatever the entity, I'll use that word, is that performs the computations, is the thing or the person, the entity that does the computing. All right, that's what this here discusses. Now let's look back at the kind of what we recognize as computational devices. All right, people can keep track of things. All right, I wouldn't call these things computers, and neither does Wikipedia. These aid in the computation. All right. You can put marks and things on sticks, and you can count them and use these as a method to assist you in adding and keeping track of where you are as you go along. To me, the abacus is a wonderful example of that. As we go along, you should recognize that an abacus plays an analogous role to manual computation that a register does inside of a CPU. Those of you that already know what a register is, in the simplest of terms, you might describe it as a thing that remembers a binary value or a numeric value. Okay, you can store a value in it. You can get it back later on. Then you can add a value to it or subtract or multiply it and things like that, right? Well, that's literally the same thing as an abacus. If you look at this abacus, this is a Chinese-style abacus. The way these things work is when these top row of beads are all up, it represents 0, and when all these beads on the bottom are down, it represents 0, and you combine the two, all right? So, for example, they tell you the value that this abacus is showing. This digit right here is a 0. So, in keeping with what I just said, this place value, this digit right here is a 0. 2 up, 5 down is 0. Okay, each bead up here represents 5. Each bead down here represents 1. So this place value, the furthest right place, the least significant digit, we call that, the most significant digit being on the left, right? If I change the value of of the digit on the left, I'm making a more significant change to this number. I'm adding a billion to the value here. If I move one of these beads up, in other words. And if I move one of the beads up on the right side, I'm adding 1 to the value that this abacus shows. All right. Now, this will come back to us repeatedly in this set of notes here over the course of this lecture series. So make sure you kind of get what's going on in here, right? You have all these place values. The way the abacus works is it's simply a way to remember a value. This right now is set to 630271548. How do I know that's an 8? Well, this one of these beads is down. That's 5 plus 3 up is 8. Okay, what's this one? This is a 0. None down, none up, that's 0. What's this one? None down plus 4 up, that must be a 4, right? And yes, that's what we got down here, all right? What do we got here? We got a 5 down and nothing up, that must be a 5, so, and that's correct. How do you represent 1? None down, 1 up, all right? So this is a pretty straightforward, simplistic concept, but it's great for a merchant in, 1601 or even 1000 BC. Oh, I want a burger and a fries and a shake. Well, I can set the price of the burger in here. Then I can add by moving these beads up and the 5s down to the value of the fries, and then add more beads, move them around to add the price of the shake onto that thing. And of course, there's always tax. Give to Caesar that which is Caesar's, right? And then, of course, you have to figure out how to calculate and add tax and all this other fun stuff. But anyway, modern day foolishness aside, this abacus was a very useful device. It probably saved billions of reams of paper. Now, remember, paper was not around. The idea of writing down in order to just add up a bunch of numbers, this was 1000 BC. We didn't have paper, right? So this was a really useful device to have, all right? Just having the ability to remember something in such a way that makes it easy to just move more beads up and down in order to add or subtract to another value is hugely useful. And roughly speaking, I mean, in all things considered, that's all you get inside of a CPU anyway. In the simplest, oversimplest of terms, that's what's going on. So this is kind of a neat basic concept. After that, people figured out with mechanical gears and things like that, you can do more sophisticated sorts of math. This thing is kind of an interesting find. It was found off of, I don't know where the heck, there's some, I don't even know how to pronounce this word. There's a map showing what? Where did there was a wreck. A boat sank somewhere. This was preserved under the ocean and then dug up, and it's supposed to be super old. And somebody figured out how to put a bunch of gears together, and they've analyzed the shape and the number of teeth and how the thing would move if they could free up these seized up parts. And they kind of figured out that it looks like these move in such a way that would explain and assist in the use of navigation by astronomical observations. So if you're, needing to, if you're a marine-based society and you need to move your boats around and it's nighttime, you can't see anything, you don't know where you are, you can look up at the stars, and then you do some math with this thing helps you do that. This is an assist mechanism. You can then kind of figure out where you are and where you need to go. All right. So this was kind of a big deal, and that led to a lot of motivation for to drive people to come up with computing devices that help you deal with trigonometry. Right. That's critical when navigating around a globe. All right. And 16, so we make this massive leap. 2,000 years later, somebody goes, hey, let's make this thing called a slide rule. Now look at this thing. This is 1620 to 30, somewhere in the 1620s. Apparently, this slide rule, or for what, we'll have to look at the attribution in here to figure out who figured that out, but in the records of history, sure, I believe it. Somebody came up with this idea with the slide rule, and it's based on logarithmic scales and things. Now, what I know of a slide rule is pretty simplistic. This slide rule, as it is showing you right now, is useful. It is in a position that represents, perhaps among other things, the ability to multiply 13 times 2 and get 26. All right, so how does that actually work? See this bottom scale here, all these little tick marks, all right? The 1 right there, the 15, that's actually 1.5. And then you have 2, then you have 3, 4, and 5 like this, okay? This bottom scale is your first value. So 1 and 3. So you see these tick marks here? There's a 1, 2, 3. You put this sliding middle part, and that's where the slide rule comes in. You put the 1 that's on the slide on top of the 1, 3 here. Okay? Then you want to multiply by 2. So you on this upper scale here, you get the 1, there's your 1.5, you got your 2. All right, this thing here, believe it or not, is called a cursor. Okay, so you then follow this back down. You don't need the cursor to do multiplication, but you do for other things. If you want to look at this scale up here, and there's all kinds of things. You can see cotangent, tangent, arctan, sines, and all that. There's ways to do all these things. But again, we're focusing on simple multiplication. What do you get when you multiply 13 by 2? Well, you put this on 1, 3, then you look over to the 2, and then you come down here and you find yourself at 2. And then you look at these tick marks in here. There's 1, 2, 3. We're looking at these bigger ones, 4. And then this giant one is 5. And the next big one here is 6. So you got 1, 3 times 2 is 2, 6. What if it's 1.3 times 2? Well, you got to keep track of the decimal places, right? And this is the same thing as 1.3. 1 and 3 gives you 2 and 6. Whether it's 26 or 2.6, it still works out. So with a slide rule, what you have to do to use one is keep track of how many decimal places you need to move the decimal point when you're done, when you're doing your multiplication like that. All right. So this is actually a pretty handy thing, especially if you actually know how to use it. Unlike me, I don't know the fundamental thing about it to use to calculate all your trig functions. All right. These were hugely useful all the way up into the 1970s. You even see, in movies when NASA, launching rockets to the moon and stuff like that. When in Apollo 11 and so on, they used slide rules to do all their math to send men to the moon. All right, this is just crazy. The thing lasted all the way up until the 1970s. And yes, in grade schools, they had a gigantic slide rule that used to hang in the front of the classroom. I went to school just after this all ended, but I do remember they still had the gigantic slide rules hanging in the classrooms. They just didn't bother to take them out. They were always up there. They're like 6 feet long, and they would show the students how to move the cursor around and do their math and all that other fun stuff. Absolutely, in my opinion, nuts that this lasted so long. It was the only way to do math. What supplanted it? Well, in the 1970s, we had effective, they had cheap desktop calculators, right? Then you still use desktop calculators today, or laptops, which are kind of glorified desktop calculators anyway. So this was a powerhouse for, hundreds of years. Okay. All right. What happened after that? So not after 1970, but while the slide rule was king, this was super dirt cheap. They made them out of bamboo and stuff like that. You can still find them on eBay and things like that. They're kind of fun to have around. I keep some in my office just as a joke. A student will walk in sometimes and ask me a question, and I'll grab my slide rule and pretend like I'm actually using it for something. Again, all I know how to do is multiply, but it's pretty funny when somebody asks, "What the heck is that?" or "What are you doing?" and that sort of thing. Anyway, feel free to scour eBay for your slide rules. Okay, so after 1620, we move up into the 1800s. All right, the 19th century is the 1800s. Some guy named Babbage, and as you know, in our computer science department, our compute servers have names like Babbage and Hopper and Turing. Well, Babbage and Turing are the guys that are fundamental that are around in the beginning of computational history. You're going to find out who they are right now. So Babbage is this guy. He was a mechanical engineer and he knew, pretty smart guy, all right? And he knew his way around gears, cogs, wheels, and things like that. And he came up with this mechanical device here, a single-purpose machine. By cranking a knob and watching these wheels go around, this thing would go through and execute certain patterns. You could set various dials and wheels and things, then crank the handle round and round and round, and this thing would eventually change the values that are on these knobs would circle and rotate until an answer of a mathematical equation is calculated, and you would then read it off those dials. This thing was called a difference engine. All right. It was used to calculate, surprise, navigational things. Again, your logarithms, and I don't know if this did polynomial equations or what, but he was kind of into that sort of thing, so it wouldn't surprise me. I honestly don't know how to use this thing. But that's what we had at the time. Cost probably a small mint, and the British government paid him to build one. So, like any good computer scientist, the immediately after finishing this, he realized that there's a much better way to do this, and it should be thrown away, and he should start all over again. So he went from the difference engine, okay, which looked oops, there's a picture of it right there, yeah. So, and of course, the difference engine was actually kind of cool. If you actually, there's some videos of this running I can't show you because of the fair use and stuff like that. I Google it. There are people that this actual one, they fire up. It's in some London museum, and you crank this handle, and all these things move around, and it's kind of neat. It actually has a printer over here that prints on embossed like cardboard that can then be taken out. What this thing does is it generates. Again, you saw a close-up of just part of this in that other picture. All these dealy wheels run around, and every time it gets to a new calculated value, it presses keys into this spool of cardboard paper over here, and it prints out a big, long strip, all right? You could take then this embossed strip, load it into a printing press, and use this to print handbills or pages in books that have tables that mariners would use to look up mathematical answers that are commonly needed to calculate heading directions and changes when they want to navigate a boat. That's really what was going on there. All right. So when he finished his difference engine, yay, everyone's happy. And he then, of course, realizes, oh, that thing's a piece of crap. I should rebuild it. I got a new idea. The analytical engine is a whole nother ball game. Well, this was all literally cast in steel and had one single purpose, and that was it. The analytical engine did things that you and I would recognize today as executing programs. It had a way to read data using punched cards, which he borrowed from some guy named Jacquard, which you can read about if you want to click on here. He was into weaving, and he built automated looms. I'm sure he put people out of work, and there were all kinds of conspiracy theories and crises in that time. However, what he did is he printed repeating patterns in cloth. Probably sped up the business by a gazillion fold, and made a ton of money, I'm sure. Anyway, Jacquard used a bunch of cards with holes in them to operate his looms. And there's a picture of him sitting in a chair. I don't see any cards or anything in that photo, but there's a bunch of pictures of these things running and videos of them running on YouTube that you can search for if you want to see it. Okay? So anyway, the Jacquard card idea was something that Babbage ran with. He says, I can punch holes in these cards. I can put that represents numbers and other such things. And then this machine, this mechanical machine, can sense the presence and absence of little holes, and it can feed cards through it to control an algorithm. In a way, and I'm kind of simplifying the situation here, I admit, each card could be used to represent one of what you and I might recognize today as a machine instruction. Do this. Next card would come into the machine. Do something else. Next card would come into the machine. Do something else, and it would continue on. All right? The mechanical device had what we might call today an ALU, a thing that allows you to add and subtract and stuff like that, perform mathematical operations. It had the ability to perform a conditional branch. It could ask a question. If X is not equal to 0, go to, some address and change the flow of execution based on the values of what we would call a variable, okay? Therefore, it had the ability to loop, and it had a notion of a memory, so it could store values. Again, even an abacus is a form of memory, all right? It had ways, you could spin wheels and things like that, and update the current state of where all the wheels are positioned in order to remember values. So that arguably, this was the first general purpose computer, because you could reprogram it, and it would function in a way that you and I recognize today as something that executes machine language instructions, all right? Now, here's this guy Turing comes along. The other name I mentioned would show up. He defined informal methods a notion of completeness, okay? If, in other words, what he did is he said, look, if you have a machine that can do certain operations specifically, it's actually, I think it's described in here, right here, in this paragraph right here. If you have the ability, and we just said what it is, if you have the ability to ask questions, to do an if and a go to of a conditional branch, right? And you have the ability to store values in memory and change them over the course of time, that is the minimum necessary set of functionality that you need to execute a program. All right. Now, this refers to something called an imperative language and gives us a definition that to me means not quite what I want it to mean or how I would define the word imperative. You have two basic types of programming languages. One of them is imperative and the other one is declarative. All right. Declarative, imperative. Imperative languages, imperative instructions are like baking a cake. It's what you and I know today. Is assembly language or a machine language? Do something. When you're done with that, do something else. When you're done with something now, do something else, and so on. Declarative language is the kind of mechanism, it's another style of expressing something. But rather than telling you how to do something, like you do with an imperative language, you're telling someone how something is to be done. That's literally what you're doing. Do this, do this. A declarative language is you describe what you want the results to be rather than describing how they are to be done. Okay? Now let's take a quick pause here. What's the what is the name of this lecture series, this course? Computer architecture and organization. Let's look at what those two terms mean right now, because it is exactly defined in imperative and declarative, okay? The architecture of a machine. Now, a lot of people misuse these words, by the way. You Google it around, you might say I'm wrong. No, I'm right. Everyone else is wrong. Go and find a formal definition somewhere of what computer architecture and organization really are. And what you will see is that, everyone just says architecture, and they refer to both architecture and organization quite often when they describe the subject of this course. Specifically, architecture is a lot like a declarative language. Architecture discusses what a computer a computer is capable of doing, right? It's what it does, all right? Imperative is like computer organization. The organization of a computer is a specification of how it does what it does. It is the combination of the two that allows you to build a machine and program it and accomplish something useful. All right? So there's these two halves to this puzzle, or this cookie, or however you want to think of it. All right? Architecture, it's what the machine does. Organization is how the machine does what it does. All right, so let's come back to here. Now that that's defined, what do we got here with this purely mechanical computer? This is entirely about how something is done. Every little wheel moves and all this other stuff. It has only one thing it can do. It's not even reprogrammable. This is a physical machine, a single-purpose machine that's a 99.99999% how it does what it does. Okay, if you want to think of it that way, I kind of do, right? As opposed to thinking at a higher level, as we say, about what it accomplishes. All right, that comes in more when you move up in abstraction and can think in terms of what we would call higher level languages and things like that. All right. So, okay, fine. So we've now formally defined what this course means. All right. So we're working our way up from the bottom up. We're starting with organization and we're moving towards architecture, we could say. All right. Okay. So what happens here? Turing complete. We just talked about that. As long as you have a certain minimal set of functionality, this guy says it is a complete system. And the concept of complete, I closed the page too early, is, well, you can read this whole thing. Spoiler alert, this whole thing will boil down to if you provide the ability to have conditional branching instructions and you have memory that can be modified and store values that change over the course of the program running, okay, then Alan Turing proved that you can use that machine to execute any formal algorithm. All right. And they define algorithms and stuff like that in here. And algorithms are much like you and I would intuit them to mean by now in your educational career. In that it's the list of instructions, the method and that you perform to execute a task, how a function comes into being and is to be performed, right? So that you have this notion here that they formally define as a universal Turing machine, okay? This is a definition in formal terms of a machine that has conditional branching and a memory that can be modified in branch instructions and things like that, right? And a set of rules that say if I build a machine and design one, and it has these basic functions, I can prove that my machine that I built is what we call Turing complete. It completes everything. It has the complete set of all features needed to be expressed as a Turing complete machine. And once I can do that and prove it, I no longer have to worry about whether or not my machine could be used, quite frankly. I know that any Turing complete machine can be used, if nothing else, to execute a program to simulate any other Turing machine. Sort of like, I'm going to fire up a Java virtual machine and I'm going to execute Java programs on my, PC. Now, your PC can't run Java, but somebody wrote an interpreter that translates Java into, say, a Pentium instruction set. Much like that, I can write a program that executes Turing instructions, all right? At which point, if I can do that at a minimum, if I can prove I can at least do that much, then Alan Turing has proven everything else I need to know, and that has to be proven, to say, hey, this machine satisfies the definition of a Turing complete machine, and therefore it can execute provably any algorithm needed to do anything that could be expressed in the form of an algorithm. Sorry for the long-winded speech there, okay? Anyway, Turing complete. If you have a minimum set of functionality, then this guy, Alan Turing, has proven that you're capable of running any algorithm on that machine. So at this point, we had a design in the late 1800s, mid to late 1800s. Wow, even before that, early 1800s, a design of an actual Turing complete machine that you and I would recognize and be capable of programming with great pain and agony, because it probably ran very slow if they even built it. Anyway, so Babbage dies before he gets his funding. His son over here, much later in the late 1800s, built some of it to prove that it would ultimately work, and successfully demonstrated at the turn of the last century, okay? That was it. That was the big leap, right? So around the same time, people were building other kinds of machines that had cogs and wheels and chains and stuff and cranks that would move around. This machine, apparently, I've never heard of this thing until we looked it up in Wikipedia here. This thing kind of calculates, I guess, tidal patterns and stuff. Again, the big money was on navigating boats. People would die, they'd get stuck and lost at sea. This was a big deal. A lot of interest in this, and you could make a lot of money by improving the ability to navigate in water. Okay, so that and the invention of a accurate timepiece. You Google that sometime. It's pretty cool. How did somebody invent a pendulum that runs accurately on a boat that is being buffeted by waves? It took a long time. There was a big financial award given to the guy that came up with that. It's kind of cool. A bunch of springs and things if you look at it go. If you're into that sort of thing, knock yourself out. Anyway, these things up here, these mechanical, so-called mechanical computers and the analog computers, very primitive, all right, but they were valuable for what they were for. In the 1900s, mostly during World War II, it became very necessary to be able to calculate things like, torpedo guidance. Where do I fire a torpedo if I want to hit something that's moving, right? Well, the militaries were huge into this. And then, of course, we had tons of money pouring in on both the Axis powers and the Allied powers during World War II to try and figure out how to best win these battles. And people, mathematicians and machinists and theorists and stuff are all getting together, coming up with these ideas and proposals. Money, of course, flowing in. Somebody in Germany came up with this thing Z3, and there's a picture of it here. What this thing does is it's got a gazillion what we call relays. They're electromagnetic things that can be turned on and off. It has two states. It could be on or off. Now we're moving into binary here. When you turn these things on and off, what happens is there's an electromagnetic, if I can zoom in, you see all these little things that look like coins, and then you see these rods sticking back here. Well, each one of these has this iron or a ferrous plate and then an electromagnet. In grade school, maybe you wound a bunch of wire around a nail and ran a battery, hooked it up to a battery, and you could see pick up paper clips and stuff like that. Well, that's exactly what this is. It's essentially an iron post with wire wrapped around it. You turn a battery on and it pulls this metal thing down. And when you turn the power off, the metal thing goes up. Now I got something that moves into two positions. That's a binary bit. And this thing moving back and forth can be used to move other things and other mechanical stuff, and it can also be used, you can't tell by this angle here, as it moves back and forth what it's really doing. There's an arm that reaches back in here and is something that is essentially like a light switch on a wall. When this thing goes on and off, this thing moves in and out, and it essentially can turn a switch on and off inside here. This is a switching system, is what it really is. So you have a way of controlling a switch with another switch. When one thing can control something else, you can then combine them in certain ways to build machines that can represent memory bits. You can add, subtract, and stuff like that. You can actually build a full machine out of it. Obviously, that's what some guy did with a ton of these relays, all right? Now, there were a couple of relay machines. They made a lot of noise and they chattered a lot of electromagnetic sparks going all over the place. Somewhere in here, you can read up on where the origin of the phrase, I need to debug a computer, I need to debug my program. Well, that came about as a result of moths that got inside what I believe was the Mark I or the Mark II. I don't know, somewhere in here it might refer to that. Just Google it, was the origin of the phrase debug. What happened was, it was in a machine like this, in a moth. The wings on a moth are really big, and what happened was, when the relay is going back and forth, the little lever reached back into the light switch that's in there, the light switch like thing. There are things on a relay that are called leaves, and they are like two hands that come together like you're praying or something like that. And in order for the switch to go on, the hands have to come together. Well, if a moth sticks its wing in there and you go to press these leaves together, they don't touch. If they don't touch, the switch doesn't go on. And now you have a bug in your computer, literally, although I don't know if a fly is a bug or a spider. I don't know what genus or species it is, but essentially that's where the phrase to debug a program came from, because there were literally bugs in there that prevented the relays from moving in the way they needed to move, okay? After this machine, there were some other machines that came out. As technology evolves, someone invents something called a vacuum tube, or what a Brit might refer to as a valve. A thermionic valve is the technical name for these things called vacuum tubes. And there's a link here I clicked earlier. There you go. There's a picture of one. If you've never seen one, they look like a little test tube like this. And inside you see these little metal thingies. The way they make them is you have this glass that's molded with these pins down here around this metal thing. And then they melt the top of what would be the test tube shut. That's why they have this little bead on top. That's when they melt it shut on top and keep the air out of it. It's a vacuumed out airless vacuum, a test tube, right? So what you have in here are these little metal plates. These wires have little these pins, we call them down here, reach up inside with little wires that connect to these metal plates, and there are little grids and screens and patterns inside these metal plates that are heated up. These will burn you if you touch them. They run rather toasty. That's why they're made out of glass, and they're pretty big. This is probably the size of your pinky finger, and these here are probably the size of your thumb, okay? Just to give you an idea how big they are. Now, each one of these is also, among other things, can be used as a switch. You can hook up power to some pins that cause it to be capable of manipulating the power that flows out of other pins on those tubes, just like these relays. So it's really not that big of a leap. Once you have invented one and say, hey, I can take what I made with these relays that physically move around and replace each relay in there essentially with one of these tubes. And the result is that rather than waiting for a physical thing to move around, these tubes react very quickly, relatively speaking. You can go up by a factor of 100 to 1 or 1,000 to 1 faster. So everybody was thrilled with that. Oh my gosh, vacuum tubes are crazy awesome, okay? A lot of people started building machines with vacuum tubes, and everybody was, happy as a pig in the pasture. During World War II, this was crazy. A bunch of guys in Britain, British did a lot of early work in computing, all right? That's where Alan Turing came from, that's where Babbage came from, and so on. Again, to deal with World War II and to crack encrypted messages from Germany. This is a kind of an interesting little story. I may digress again. This is history, why not? What happened was, and how it relates today, it's a lot like mining for cryptocurrency, Bitcoin mining. They noticed that Germany was broadcasting messages that were in code, so they're easy to intercept these radio broadcasted messages over the airwaves up in Britain, or at least certainly in France. And when they would hide in Europe, they could hear these radio broadcasts, and they would write these things down, but they didn't know what they mean because they were literally encrypted. All the letters were substituted out, and they used the Germans used a machine called the Enigma. There's a movie called the Enigma, and another movie called U-571, and another there's a whole series of movies about what happened in this place called Bletchley Park in Britain during World War II, when Alan Turing and a bunch of guys came up with this idea that they called the bombe, the B-O-M-B-E. Which, and there's a picture, awesome. It looks like this. And what the bomb is, if you know what brute force attempts at logging into a computer is, that's what this thing kind of did. All right. So what would happen is they would intercept a message over the airwaves, and it was encrypted. It was encrypted German. So what they needed to do is they needed to figure out essentially, in the simplest of terms, what is the password for the encryption algorithm. You can watch the movie U-571 to find out how they figured out how the algorithm worked, how the Enigma worked, how the encryption was done, but they still needed the password. Then Germans would change the password every single day, so they had a lot of them to undo. Well, Alan Turing came up with a simple solution: try all of them. And I'm kind of oversimplifying it, but he came up with an optimized way to continuously try every possible password until a message became recognizable. All right. And once they had that, they had the password that was good for a day. And then tomorrow there'd be a new password. They'd fire this machine up. And what it would do is every one of these wheels would just essentially try every possible password until all of a sudden a message looked like it was readable. After a while, Germany upped their ante and came up with a new encryption scheme that was better. And then Britain had to come up with a new machine. This one was called Colossus. And this machine is pictured here. The bomb, as you saw, was a bunch of motors and gear wheels. Colossus, on the other hand, looks like this. And it has a bunch of these vacuum tubes, or what they would call valves. And it had a paper tape, a punched tape rather than cards. It's easier to have one big tape on these wheels and a motor. This thing spins pretty quickly. If you Google around, you'll probably find a video of a recreation of the Colossus machine actually running. These wheels are spinning pretty darn fast. And what's on this tape are the actual instructions in the order in which they are to be executed. So this is an endless loop. It's a really big, long loop of paper that goes around and around and around. And each time this paper goes through is one loop of executed instructions that are all punched in the holes on this tape. And this little black thing right there is what reads the tape. Again, I've seen a modern video of a rebuilt version of this thing running, and the guy explains how it all works. So if you're interested, Google around, you should be able to find that. It's kind of an interesting thing. Again, all motivated to decrypt messages by these guys in Bletchley Park. A book just came to mind that's called Hut 13, which also describes activities in Bletchley Park. They had these huts. There were different buildings. Each one of them was called a hut. Hut number 13 is where some, I don't know, high and mighty crypto stuff was going on. Anyway, again, during World War II, the United States wanted to build a machine to calculate navigational charts and things like that. Somewhere in here it talks about what they wanted to use Enigma for. It can solve complex problems. It can do 5,000 mathematical operate. It can add and subtract 5,000 instructions per second, which was, as they point out, 1,000 times faster than any other machine. Wouldn't it stink to only be able to do 5 things per second? Yikes. Boy, I sent a text message with that. No, thank you. So this was an exciting machine. It can multiply and divide as well. The way you program it is you move around all these cables, all right? Oh, I want to change my program. Give me 6 hours to move all these plugs, all right? Then turn it all back on, and it'll be doing a new thing. So it's reprogrammable, and it's mostly tube based, I believe. I think it also had what we call core memory, which were magnets that could be charged with magnetic fields that would stay magnetized over the course of time. So later on, another sensor could go back and find out if it's magnetized or not. Not unlike how floppy disks and hard drives work today. We are just magnetizing little spots of metal on spinning disks, and the disk drive head is the thing that goes and senses whether they're magnetically charged or not. So that, again, is based a modern version of what we called core memory back a long time ago. Okay, so modern computers. All right, it's fun of the ancient history, right? The things that happen today are, so we still are concerned about universal Turing machines, okay? This is still the essence of everything that happens today. When most of us use imperative programming language. And when I say most, I mean like 99.9% are imperative language. Everything, COBOL, Fortran, Python, all this stuff. Non-imperative languages are things like if you ever created a makefile for your own project, you'll notice that thing does not fill up with if-then-else's and procedural statements. It has sections that are procedural, but they're not a procedural thing. What it is it's a set of, oftentimes the word recipe is used to describe the things that I need to have created somehow. How do you make something out of something else? So you don't really think of it in terms of the sequence of events like you do in an imperative language. So makefile is probably a pretty good example of a declarative language. All right, you're declaring the files you want something to create for you. Okay, now you could also argue, like I said, it also includes tiny little procedural sequences like baking recipes and how to make various pieces. And those little thingies are all combined by the declarative aspect of a makefile to create what needs to be created. All right? Okay, so some other names like von Neumann. This guy here in Princeton designed a machine. The von Neumann architecture is named after this guy, obviously. That is the kind of machine we'll be discussing in this class. There's another one called a Harvard architecture. If we have time, we can talk about that one as well. They're similar, but not the same. What happens over here? Stored programs. Again, things start looking more and more recognizable. Machines that have an instruction set. This thing is, again, back to the architecture and organization. The instruction set is the line that separates the architecture from the organization. Quite often, an instruction set is considered the architecture of a machine. How these instructions are done by, you have tubes in there, you have relays, how is the machine wired, how many registers are used, does it have multiply instructions, how does multiply work, how does adding work, how do you shift, do you have a barrel shifter, do you have a clock shifter, all that other junk, how these instructions get executed are organizational aspects, all right? So that's where the demarcation is between the two words used in the title of this thing, the architecture and the organization, right? Okay, so as you wander down here, you'll start seeing here now we actually have stored programs, and you could store them on in a way you could you had to have memory. So some people used glowing phosphor, the Williams tube. It was a thing that would glow, and that you could then have light sensors to determine whether or not a part of what is essentially an old cathode ray tube TV screen was glowing or not, and that was a 1 versus a 0. If it's black, it's 0, and so on. And the phosphor on the screen would remain glowing for a long period of time, and it would be used as storage. That's how they did it with that particular machine. You could also store things if you had enough relays. You could store things you could actually punch paper holes in a thing and then loop in the Colossus machine if you wanted to. You could put both a punch and a reader in here, so that it could actually have a punch down here. It could punch holes that could then come back around and then be read if you wanted to. It's not entirely unlike, and I'm taking a lot of liberties here, how a disk drive might work. Now, a paper tape can be punched only once, but a disk drive can be remagnetized over and over again. Every time the disk spins around in a circle, it can reread back in what it wrote the last time it went around, so to speak. That's a form of memory, certainly, that we're all familiar with. Okay, so the machine's down here. Once you go from vacuum tubes, you start dealing with these things called transistors. So in the 50s, but I guess it was in the end of the 40s, Bell Labs, the American telephone company, part of it, came up with this thing called a transistor. You can read about that in various historical recollections of how Bell Labs functioned in the 1900s, and how they discovered things like the bipolar junction transistor, which you can still buy today. These are still manufactured to this day. These things do the same kind of thing that a vacuum tube does. Therefore, transistors just immediately replaced vacuum tubes. Why? These are tiny. This is a super duper teeny little thing. Do they tell you how big that is? No, that's a KSY34. That's the type of transistor. Okay, great. But that's pretty darn small. Nowadays, they make transistors so small that there are on the order of 3 billion of them on your i7 processor in your PC, all right? The Intel processors that you all hear about in your PCs have on the order of 3 billion of these in them. That's how small that is. And the CPU inside your PC is a roughly 1 inch square, if that. Probably not even that big. They're tiny, okay? Vacuum tube, each one of a vacuum tube the size of your thumb, that's crazy. Plus, they're super hot. No. So very good riddance to vacuum tubes and relays and stuff like that. So along with shrinking in size, we find they use less power, they give off less heat, which is due to the less or the reason they use less power. They're far more reliable. They can run faster and so on. In every way, shape, and they're cheaper, and they don't wear out and so on. Anyway, this website now wanders off into different kinds of transistors. And then if you put many transistors together on one single thing, right? So what this is here, that's a piece of silicon with one transistor on it. Well, if I got a bigger piece of silicon over here, I can put another transistor. And if I get a bigger one yet, I can put another one over here and another one over here, and then I can connect them together. These little thingies, these little fingers coming in here are the wires, like those tubes have those pins sticking out. Transistors have pins that come out. This is one of the pins. Down here is another one of the pins. Well, I can, if I have multiple transistors that need to be connected together, I can just connect them together all on the silicon. And keep going and adding more and more and more. And like I said, today we're on the order of billions. The biggest chip made last year, there was an announcement that someone actually put 1 trillion transistors on one single chip. Holy cow. And that was last year. Who knows? Are they up to 2 trillion by now? Just insanely huge numbers of transistors. Anyway, you can do a lot of work with a transistor, as we'll see as we move forward over this semester, okay? That's what an integrated circuit is. Basically putting many, many transistors all in one thing that have a combined purpose. So rather than working with the discrete little transistors and wiring them all together, we can work with multi-function integrated circuits, and we call those things give them names like microprocessor or a memory. Memory has hundreds of millions of if not billions of transistors inside of it to hold all the memory bits and so on, right? The idea of a microprocessor kind of came out and then in the early 1970s. And by the 1980s, it was well on its way. You had all these familiar names like Apple and Microsoft, and DEC was around, IBM, and so on, and they were all using these microprocessors that today we still use them. The big Intel chips started in the late 70s with the 8086 chip, and that's the same family that they're still making today with more functionality and faster and so on, right? Today, nowadays, your phone, you have what are called ARM processors. That's a different kind of technology, or rather, it's the same kind of technology. I guess it's still a microprocessor on an integrated circuit, but a different company. It has a different instruction set. It has a different organization, okay? So there's the history of computing, arguably, ending with today. And as we move forward in this class, we're gonna see how some of this impacts decisions that are made when we talk about how we program machines and stuff like that. So thanks for watching. See you next time. Bye.